This is Introduction to Ka and Kb, Section 4.8, Acids and Bases for Chemistry 12. We'll start by talking about what is a weak acid. So a Ka is an ionization constant for a weak acid. They don't ionize 100%. These are not your top 6 acids in your table. What it means is that instead of 100% ions, we might have 95% actually the whole acid and about 5% ions. Okay, what that means to you in terms of numbers is a little note over here. You cannot use the molarity to find the H3O. For example, if I gave you 0.5 molar of a strong acid like HCl, you would know that your H3O concentration is the number 0.5 molar, and you could use that in all your calculations. You cannot do that with a weak acid because this here is not 100%, which means we don't actually know what that number is. We will have to calculate it. To start by doing that, you're going to work out your Ka expression, which is products over reactants for your acid. H3O plus here on the top, that's on my product side. That tells you you're working with a Ka over my acid. Notice the acid's got the conjugate H on the end there. And just a quick note to remind you that the water doesn't count. I've put a note over on the side if you need to pause and copy it in. It is your only liquid, so you do not use it like we have used for our entire Ka and KEQ units. The next part that you can do is get your acid-base table. If you don't have it handy, you can get a value for Ka from your table. So I'm going to go to your table. And this is our acid side here on the left, and you're just going to read down until you find your ethanoic acid, or acetic acid more commonly, which I underlined in green. We've got the number 1.8 times 10 to the minus 5. So I'm going to put that number into our notes. 1.8 times 10 to the minus 5 is the Ka for that acid. So these numbers here, they come from your table, and you can look up any of your acids. Just make sure to look down the left-hand side, which is the acid side. Okay, so the stronger the acid, the greater the Ka, and this is what we've been calling product heavy throughout our course. And the greater the Ka means more ions, so more H3O, and that's also going to contribute to a lower pH, which we'll talk about in a couple of lessons. Okay, the same is true of a base ionization constant. I'm going to do my bases in blue, so I can write a value for Kb. In this case, it would be NH4 plus times OH minus over NH3. And again, the stronger the base, the greater the Kb. So we'll move to an example calculation. What is the H3O of 0.25 molar CH3COOH? So remember, it's a weak acid, so your H3O is not equal to 0.25 molar. So there's some more calculating to be done on these. So to start with, we will write our Ka expression. Okay, and we got the value we know from our table. That was 1.8 times 10 to the minus 5. And now we have to decide what we're really looking for here in this expression. We want to know the H3O. So this is what we're looking for. So we're going to call this X. And these are 1 to 1. So we're also going to be able to call CH3COO minus X. Okay, so then you need to bring out your ice table. The time that you're going to use your ice table is if it's a weak acid. So use with weak acid. If it was a strong acid, you just use the number given in the question. All right, so we know that we started with 0.25 molar CH3COOH. I should read H2O here. And other things we know, we start with these at 0, just like KSP. We want to start with before it ionizes. These will be plus X and plus X because they are 1 to 1. This would be minus X. 0.25 minus X, X, X. So there's my ice table. Now I need to put a little note about this value. Just going to pause while I fill this in. Okay, I've put quite a large note here. You may need to go back and pause my video where you fill in this little piece here. And it has to do with this value here. Since the CH3COOH, that's our acid, does not ionize very much, X is very small compared to the original number. When calculating the answers, X becomes insignificant. So what we do is say that this number is approximately equal to 0.25 molar. And we continue on our calculations with 0.25 molar to make it easier in the math. As you move on in university, they may ask you to prove that your X was insignificant, and you will do that by a percent difference, and if it's less than 5%, I believe, it means your assumption was correct. We do not cover that in Chem 12, but I can show you how to do it if you need to know later. Okay, now what we're going to do is we're going to go back to our Ka expression here. I'm just going to write it back out because mine's a little farther away. Okay, I'm going to fill in what I know. I know my value for Ka was 1.8 times 10 to the minus 5. Remember, I got that from my table. I know my top is X and X, which will be X squared. And I know my bottom is 0.25. Okay, so I can calculate all that out, and I can solve for X. X is equal to H3, oops. X is equal to 2.1 times 10 to the minus 3 molar, which we can remember is what we were solving for, which is our H3O plus. Okay, so in this guy here, if you want, you can call this X squared in your calculation. Same thing. Now, the significance of H3O plus will come along in section 4.10. Later, we will use this to calculate the pH. To find pH using, wait for it, logs. Okay, I know that doesn't make you too happy, but it's a fairly simple log operation. Okay, we will see you next time.